The ability to accurately localize high-density EEG to an individual's cortical surface allows new approaches to high-resolution functional connectivity studies with both spatial and temporal resolution. BEL scientists, led by Mariano Fernandez Carraza, are working with Sorcerer's advanced EEG localization to examine networks of functional connectivity. Functional connectivity networks are now well known from fMRI studies. However, electrophysiological functional networks can now be examined with phase-amplitude coupling analysis to reveal the oscillatory dynamics of both local and global cerebral networks. Phase-amplitude coupling analysis reflects the interactions among neural networks in which the activity reflected by high-frequency oscillations, such as local gamma networks, is organized or modulated by low-frequency oscillations, such as theta, from larger, more widespread cerebral networks. The high-density EEG collected during sleep is first source localized to the individual's cortical surface, which, extracted from the individual's structural MRI, allows the construction of an accurate head conductivity model unique to that person. To simplify the computation of phase-amplitude coupling across the standard functional connectivity networks, we group the large numbers of cortical surface dipoles, such as 9600 sources, into Brodmann areas. To compute the functional connectivity networks to functional connectivity fMRI standard networks, we then compute PAC, phase-amplitude coupling, for each of the major functional networks, such as the default mode network, ventral attention network, and so on. In addition, we can compute diffusion tractography estimates of the neural fiber tracts connecting cortical regions, here we use FSL, and then examine the covariance of electrophysiological oscillatory coupling in relationship to specific neural fiber tracts. With the advances in HD EEG and anatomically constrained electric source localization, it is becoming increasingly feasible to examine functional connectivity networks with both the spatial resolution of HDEG cortical source localization and the temporal resolution inherent to the brain's electrophysiologic activity.